In our previous lesson, we talked about the mathematical relationship between pH and the concentration of H3O+. Plus, we also learned that we can use POH as a tool to calculate the concentration of the hydronium ion, or the concentration of the hydroxide ion. In reactions such as this, where we have one substance interacting with another, and that substance then loses a proton which it then gives to the other substance, this substance, HF, is behaving as though it is a Bronsted-Lowry acid as a proton donor. Typically in reactions, a Bronsted-Lowry acid will also be accompanied on the product side with its conjugate base. The conjugate base simply differs by a proton. Since the protons are positively charged, every time you lose one, that conjugate base becomes negative by that factor. These two substances, because they only differ by a proton, are considered to be a conjugate pair. Now, in this particular interaction, we also have water accepting the proton from the HF. So in this particular situation, water is behaving like a Bronsted-Lowry base, and its conjugate acid is the H3O+ that's being formed in the products. Again, this is also a conjugate pair. Now, in this particular situation, we have NH3, which is interacting with water, but the NH3 is actually taking a proton or stealing one from the water to form ammonium, or NH4 positive 1. Since this substance differs by a proton because it has one too many protons, its charge goes up or becomes more positive. In this situation, ammonia is behaving as the Bronsted-Lowry base, forming its conjugate acid, and these two substances exist as a conjugate pair. The other substance, water, because it is giving its proton to ammonia, is behaving like the Bronsted-Lowry acid, and the substance that it forms is its conjugate base, which is the hydroxide ion. These two substances together form a conjugate pair. Now, when we're piecing together a reaction such as this one, where we talk about fire ants using formic acid as a defense mechanism, when formic acid interacts with water, it behaves as though it's a Bronsted-Lowry acid. So this is the chemical formula for formic acid. It interacts with water. Now, if it's going to behave like an acid, it's going to donate a proton to water, which is going to form hydronium. Whatever's left over is going to have a -1 charge because it lost one of its protons. The first conjugate pair that we can see here is the Bronsted-Lowry acid, formic acid, and its conjugate base, formate. Water is doing the reverse. It's gaining a proton, so it's behaving like a base. Its conjugate acid is H3O+, and it also exists as a conjugate acid-base pair. Nicotine, on the other hand, acts as a weak base. Weak bases typically are carbon-containing compounds that also contain some nitrogen. When this substance interacts with water, it's going to do the reverse. Since it's behaving like a base, it's going to take a proton from water. Water then becomes hydroxide, and nicotine now has one extra proton, which causes its charge to become more positive. The first conjugate acid-base pair that we can see here is nicotine with its conjugate acid. That's one conjugate acid-base pair, and water, since it's behaving like a Bronsted-Lowry acid, is forming its conjugate base, and these two substances also exist as a conjugate acid-base pair. When we're trying to predict what the conjugate of a weak acid or a weak base is going to be, it really just depends on whether it's behaving like an acid or a base. Since all of these substances are interacting as though they are weak acids, HF, if it interacts with something else, as an acid, it's going to donate its hydrogen to the other substance, and its charge is going to decrease by the number of hydrogen ions that it lost. The same thing is going to hold true for hydrocyanic acid. It's going to lose the one proton that it has, and it's going to form Cn-1. Now, if we look at sulfuric acid is a diprotic acid because it has two hydrogens that can be lost. If we're only looking for the conjugate of this specific acid, it's only going to lose one hydrogen at a time, so the conjugate base of this acid is simply just HSO4 with a -1 charge. Finally, we have the ammonium polyatomic ion. It has 4 hydrogens, and it has a positive charge already. If it loses one of the hydrogen atoms that it has, it's going to become NH3, but the positive charge is going to come back down to be a neutral charge because we're losing some positive charge. So the conjugate base of that acid is NH3. Now, if we're looking at the reverse situation where we have a weak base, HCO3 - 1 is the bicarbonate ion. If it gains a proton and behaves like a base, its charge is going to become more positive by 1. So its conjugate acid is going to be H2CO3 without a charge because it gained a positive charge. HPO4 - 2, if it gains a proton, its charge is going to become more positive. H2PO4 with a -1 charge. There should be a -1 next to this symbol right here. This would have a -1 charge. The next substance that we have here is a nitrogen-containing, carbon-containing compound. If it gains an extra hydrogen, its number of hydrogens is going to change to an 8, so this should actually be an 8 here, not a 7. 8 with a +1 charge. And finally, this compound here, if it gains a hydrogen, is going to become a little bit more positive, CH3NH3 with a +1 charge. That concludes our discussion of conjugate acid-base pairs. Our final topic will be neutralization reactions for acids and bases.